So let's continue with the remaining part of the software issues of additive manufacturing chapter. We were discussing the slicing, since we said that slicing is the most important part of additive manufacturing and is always directly related to the computer science, computers, and some other software. And in slicing, what we do, we have three main algorithms. In the first one, we check the intersecting, let's say, triangles with the slicing plane. We find that intersecting portions. And then in the second algorithm, we combine these line segments so that we have the contour of the slice. And then in the third step, in the third algorithm, according to the given, let's say, specs, we try to fill the interior of this contour. Okay, and I don't want to go through this flow chart, and this is for slicing. And then in slicing, we have the most important part here, storing the intersection lines of the faces on the plane. And for determining the intersections, we have 5 cases. And in the fifth one, we have some intersecting portions. So with the help of some calculations, we can determine that these portions. Then in the ordering part, we check the tails and the heads of the line segments and try to obtain a contour, a connected contour. And in the filling part, we simply fill the interior according to our algorithm. This one, if you remember, is filling the interior with simply horizontal lines. And even not zigzag, but by doing some modifications, we can have a zigzag version of the same algorithm. But if you look at the CAM software of different types of additive manufacturing machinery, you will see that in addition to zigzag or just simple horizontal lines, we have tens of different filling patterns. So now let's focus on some different issues about the software in additive manufacturing. Depending on the technology you are using, whether it's an fused filament fabrication, stereolithography, or powder bed systems, we may have some variations in terms of this slicing. For instance, in powder beds or in SLA, the interior should be completely, let's say, filled. You should completely be curing the internal material. But in fused filament fabrication, as you know, we may have just 20% infill or just 10%, but this is not valid for the other technologies. Another issue we can consider is the relation between the slices. For most of the time, we don't have much change between the consecutive slices. They are very similar, just some maybe internal structure or some coordinates are modified. But if you consider 2.5D shapes, which are the shapes actually just obtained by extruding 2D drawings, these are called as 2.5D objects. And in such cases, the slices are exactly the same. Since what you are doing, you are simply extruding the 2D slice in 3D. So instead of storing all the information, maybe doing all the computations for each slice, you can do it for a single, let's say, Z value, and then the other ones will have the same contour. So this will save you lots of time. Another issue we didn't discuss is the support structure generation. And in the slicing part, you need to have actually maybe one more algorithm to check the slope of the surfaces. Depending on the angle, you may need to put some extra support structures underneath. So this is an important issue, especially for SLA systems, FFF systems, and some specific powder-based technologies. So in here, we can simply consider the normals of the triangles, and according to their angles, we can comment whether there's a need for support or not. And another issue about support structure is that sometimes you may need to have support going to the base downwards or going to the part itself. Depending on the complexity of your part, your algorithm should decide or the user may decide whether the supports are going to the base or just to the surface. And sometimes you may generate a specific special STL files or support structures. You don't need to do it in the, let's say, slicing stage. You may do it in the design stage. So there are also such cases, but this is not common. For most of the time, we prefer to generate the support structures in CAM software instead of in doing or generating structures in CAD software. And we mentioned about the filling patterns. They're important, and you may have special algorithms for them. And if you remember this simple shape, we have a very simple zigzag pattern. But if you remember, we have 3 portions. Cannot manufacture it by using a continuous, let's say, infill path. We need to have more paths inside the part. And if you remember, we said that having a continuous pattern, having a continuous infilling path is obviously preferred, since you gain time and you decrease the any errors you might have in the possibility of errors you might have in the extrusion or in other, let's say, manufacturing processes. And I want to briefly consider once again the problems you have with the STL files. We know that they are quite simple, but still there might be problems. First of all, you already know that we don't have any units for the STL files. Depending on the type of actually the software you are using, they may consider the STL file in millimeter, in inches, sometimes meters. So you should be careful about it. For instance, if you make a mistake between inches and millimeters, then your part might be 25 times larger, or depending on your conversion, it might be 25 times smaller. Another issue, since the origin, the coordinate system of the STL models, as you know, is at the bottom left corner. So that might be an issue for your machinery. You may need to shift it on your CAM software. And we know that in STL files, or the coordinates must be positive, since the origin is at the left bottom corner. So the rest will be obviously positive. And we have other issues, other problems. We have actually kind of a rule in the triangulation. This is the vertex to vertex rule. And as you see in this example, we have a problem vertex here. And according to this rule, the vertex to vertex rule, we need to have triangles sharing 2 of their vertices. And this is as you see, a must. Each triangle should be sharing 2 of its vertices with the triangles adjacent to it. So neighbor triangles should be sharing 2 vertices. Can anyone tell me the problem here? What is that problem? So let me number these. This is the first triangle, the second, the third. Can anyone tell me the problem between these triangles?
Sir, we must pass same vertex 2 times.
I couldn't get it. Can you tell it again?
While scanning, we must pass the same vertex 2 times.
What do you mean by scanning? What are we scanning?
Türkçe açıklasam olur mu hocam?
Okay.
Line'ları soldan, yani daha doğrusu saatin tersi yönünde STL files'ı scan ederken, hani taratırken tüm line'ları
such operations and scanning the STL file is only scan for the triangles. We don't have any such scanning in STL files.
Hocam merhaba. İkinci ve üçüncü üçgenlerin normalleri aynı olmak zorunda. Çünkü ortak bir noktaları ve bir line'ları var. O yüzden yani boşu boşuna ikiye ayrılmış bir üçgen olabilir mi onlar?
Obviously, yes, we don't need to have actually this line. This is unnecessary, but can you show me how we are actually conflicting with this rule? There's a rule, as you see, vertex to vertex rule, and we know that this is a problem which is violating our rule. And can anyone tell me how this point, how this vertex is violating the rule?
Ben söyleyeyim hocam. 2 ve 3 üçgenleri birbirine bir tane kenarda kesişiyor. O iki üçgen aynı zamanda 1 ile birer kenarda kesişiyor. Bu şekilde olduğu için gereksiz oluyor.
Okay, but which triangles, then let's say, which triangles are violating this rule?
Triangle 1 and 2 doesn't share two vertices as well as 1 and 3.
Yep, you're right. This is actually the answer I was looking for. If you look at the first triangle and the third triangle, they just share a single vertex, right? They don't share a second vertex. But according to the rule, they should be sharing at least, not at least, but they should be sharing two vertices. And we don't have any problem between the second and the third one since they share, as you see, two vertices. That's fine. But if you look at the first and the third triangles, they only share this one. And we have another problem between the first and the second one. They are only sharing this upper vertex. This vertex is not belonging to the first triangle, and that's why we have the problem. And as your friend, one of your friends pointed out, this is unnecessary. We don't need to have such a line in between second and the third one and decrease the number of triangles we have in this plane. So if you make it like this, oops, I couldn't draw it properly, but assume that this is, let's draw it once again. Yes, if you have such a case, such a plane, and there is no problem, and you see that they share two vertices. So this is vertex to vertex rule. If you have such a problem, then that might actually be problematic also in your slicing stages. So you should be careful. And if you are using a proper software, they shouldn't have actually such problems. And they are also checking this vertex to vertex rule.
Hocam bir şey sorabilir miyim?
Sure.
Böyle bir problem çıktığı zaman peki manuel falan mı düzeltmek gerekiyor yoksa direkt farklı bir software kullanmak mı gerekiyor?
There are some mesh mixing software. I think they're called Mesh Mixer, Mesh Lab. There are such special software. Even I think Microsoft has one, NetFab. And if you have problems with your STL file, NetFab is, I think, an online service. You can upload your STL file to cloud, and then they will fix it for you, and then give the proper STL file for you. But as I mentioned, this is a very rare problem. And this happens usually once you have highly complicated shape, like you have, let's say, lattices like truss structures, or you have thinner shapes, then you may have a problem. But generally, for about 95% of the time, your STL files will be proper.
Sağ olun hocam.
Hocam peki bu sorun çözülmezse ne oluyor? Yani tamam dediniz böyle problemler olabiliyor. Peki biz bu STL file'daki bu sorunu çözdürmezsek ne oluyor somut olarak?
Not big problem, especially for the vertex to vertex rule, but we will see another problem. The second one is more problematic for slicing for additive manufacturing. This one is not that big issue. You can handle it while slicing, but the one now we are going to see, the leaking STL files are big problems. If you have a leaking STL file, then while doing the slicing and while obtaining the contour, you may not be successful. If you have, let's have a look at the details of this rule, and then I will mention some problems. So the second rule is the leaking STL files. Your data file might have some non-manifold entities, which means that they're not manufacturable. And this is checked again according to a rule, and this rule is called Euler's rule for solids. I'm sorry. This is the simple rule. According to the Euler's rule for solids, the number of faces minus the number of edges plus the number of vertices should be equal to 2 times the number of bodies. Okay, let me do some example with it. The simplest body is tetrahedron, so that's why I'm going to work on a tetrahedron again. Not okay. It's much better. And we have another line at the back side. Yes, this is our tetrahedron, right? How many faces do we have? And this is a tetrahedron and still an STL file, right? Since all the faces are represented with triangles. So what about the number of faces? How many of them we have?
4.
Yes, as the name implies, it's a tetrahedron, so we have tetra faces. What about the number of edges?
4.
Again 4.
Yok, edge dediniz değil mi hocam, pardon. 6.
6.
1, 2, 3, 4, 5, 6. Yes. This is 6 edges. How many corners or how many vertices?
4.
Yes, we have 4 vertices. So let's check whether this is fine. And it is 2, which is equal to 2 times 1. Since we have just a single body, so we can say that this is okay, there is no problem. But let's have a look at a bit degenerated case. I will try to draw, but I'm not sure how it's going to be. Let's have this one here, and then have a bit modification here. This is the front side, the right-hand side, and we have the same back edge at the back side, okay? So the problem is on this face right now, okay? We have a bit leakage here. So which means that this is open, not a watertight model. We have leakage here, okay? And now let's try to check this rule. Again, how many faces do we have? This time we have one more face, right? Since I divided this right face into 2 triangles. This is the first one we have here, and the second one is here. So we have one more face, 5. Now, how many edges do we have? Initially, we had 6 of them, but right now we have 1 extra here and 1 extra at the center. So what is that? It becomes 8, right? What about the vertices? Actually, we should be assuming this one is a single face, not 5. This should be 4 faces once again, just it has an opening. And then how many vertices do we have? 4 of them, and then we have an extra here, 5 of it. And what is that value? This is 1. And this is not equal to 2 times 1, which is the number of bodies. We have a single body, but we have leakage there. So let me draw this one here, the sides face, let's say. This is the kind of face we have there. And assume that your software was not successful and it generated such an surface for the right hand side. and you have a leakage here. If that's the case, this one is a leaking STL file, and you shouldn't be actually continuing to manufacture with the STL file. What happens if you, for instance, take a slice here and then determine the contour? Let me try to draw it from a top view. Yes, that will be the contour you have, which is, as you see, not complete. We have a gap, and in printing, as you know, since we are printing some kind of solids, we should have a complete contour. This is not complete. This is a kind of line. So we cannot say that this is a polygon, and we are going to have problems, especially in taking the slices.
Hocam, I couldn't understand the number of edges.
Number of edges.
Yes.
Okay, you can simply count. Initially, it was 6, and now we have at one more here and one at the center. Actually, not center, but this 2. This is the additional one, and the other one is another addition. So we have 2 more edges added, so we can say that this is a leaking file, and you need to be careful about it. So let me count once again. We have 1 here, 2, 3, 4 here, 5, this vertical one, and we have 1 at the back side, right? But instead of having this triangle here, if you have such a triangle, you will have 2 more edges. This will be the 7, and the bottom one will be the 8th edge. And these are already counted. This is the second one. This is the third one. So now the number of edges is increased to 8. So why do we have such problems? Your friend is asking. The CAD software is not successful in, let's say, converting an, I don't know, let's say SolidWorks file to an STL file, and it may be doing some, let's say, mistakes while triangulating the surface. So you may have, let's say, a complicated surface like this one, and while doing the triangulation, they may fail. So it's not an easy task. It's a bit complicated, and some of them may fail, especially while they are dealing with very small, let's say, shapes, having detailed features. So while doing this triangulation, they have problems, and the resulting STL file might be leaking. And as I mentioned, we have some special software for fixing such problems. Even there are online cloud software for that. And this is not common, about just 9, maybe less than 5% of the time you face such problems. And I think some CAM software, I'm not sure, but Cura might have a fixing tool inside the software itself. And I will show you another CAM software today while we are discussing the stereotypography. And in that software, I know there is an STL fixing tool. And before doing the slicing, you check it, and it gives you some errors if there are leaking regions. Any questions, guys?
Hocam, with this rule, we can find that there's a problem, but can we locate the point of error?
No, you cannot do that. This is just a simple rule stating whether you have leakage problem or not. But to determine the position of the problem, the level, the height of the problem, then you may need to do some checks. You may do slicing, try to obtain the contour. If you don't have a close contour, then that means you have a problem at that height of the object. So if this rule is not true, then we can say that the file is leaking and it's not watertight. You cannot keep water inside. And we call these faces as degenerated faces. And as you see here, this is sometimes due to numerical truncation and sometimes due to triangulation. In some other cases, if the part is very small, you may have an very small triangle, which has actually 3 vertices, but their coordinates might be the same. They may have the same coordinate values. So if that's the case, obviously the easiest solution to ignore this triangle and then continue with the rest of the triangles. Yes, some CAM software detect these errors and they warn you, but as I mentioned, some of them do not have such properties, so you may need to check them in advance and don't have such problems during slicing and manufacturing. So yes, simply if you have such problems, you can remove these triangles and do some maybe modifications, connect new edges, new corners, new vertices to the proper ones, and continue with the rest of your fabrication process. And as you know, STL files are storing the information about the triangle, so it's not easy to do the modifications on the file itself. Since if you, let me draw a kind of an, let's say once again, a cube here. Assume that this part is triangulated, and if you simply change the coordinates of this vertex, let's say up to here, then what is going to be, we'll have a new triangle here, but the other ones will not be modified. So which means that, again, you will have some overlapping triangles or a space which is not covering any volume. So doing modifications by just working on a single vertex is not possible. There are some other files which is possible, but in STL file format, you cannot have such radical changes. What you are going to do, if you want to really have such a modification, then you need to update some other vertices also in the file. So this will be quite challenging and you need to spend more time. Or you may do some little modifications. You may add a new portion, let's say having another cube beside is not that difficult. You can easily merge them together. So it's what you're going to do. You will add the triangle information about this new part to the end of the file and do maybe have extra triangles here, but it doesn't matter. You may still have just 2 triangles which are representing the base and then put some other triangles on this part. So little modifications are possible, but the complicated ones, the radical ones, are not easy to do. So if you don't have an access to an original CAD model, then you don't have another option, obviously. You should be working on the STL files, or there are, as you know, some CAD softwares are capable of converting these triangulation files or STL files into their native file formats. But they will not be fully functional. And online, we have some class sources for STL viewers. You may just upload your model to a web browser and do some modifications, view it, and if there are any leakage, any problems, you can fix all these problems online. So what we are going to do, we can do shifting is the easiest thing we can do on the STL files. We can simply add values to the coordinate values, and with that way, you will be shifting your part to somewhere on the plane. And the easiest thing we can do is to scale them. Since the file is unitless, by simply multiplying with some values, you can easily scale them. You can rotate them. Once you do rotation, obviously, you need to modify the normals. And another easy thing we can do is to merge them together, or sometimes we can also divide them to smaller parts. Why is that? Since your printing volume might be smaller and you may not be able to print a large part, that's why you may need to do some segmentation. And these simple operations can be done right on the AM software, or what we call computer-aided manufacturing software, CAM software. They can be done on the CAM software, like checking the integrity, which means that checking whether the given file is watertight or not. You may add some support structures, as you know, do some optimization on the difficult parts, add features like add text on the STL file, maybe do some remeshing, do segmentation or union merging operations can all be done on the CAM software. You don't need to go back to the CAD tool. These all can be done on the CAM software. And we can do Boolean operations. What are the Boolean operations? They are simply union, intersection, and let's say difference operations. We can perform these operations on the parts and try to have more complicated designs. Again, instead of going back to the CAD software, we can do it on the CAM software. Any questions, guys, about the STL files or other issues we discussed up to this point?
Hocam bizim bu hani çok basit bir parça üzerinde gösterdik ya yüzeyleri ve kenarları, köşeleri belirlemeyi. Bu komplike bir parça olduğunda normal vektörlerini yüzey olarak mı sayıyoruz? Ya da aynıysalar yüzeyi eliyor muyuz? Aynı normal vektörüne sahip iki üçgenin.
You cannot actually remove triangles. If your CAM software is just working on the triangles, even though they have the same normal, you cannot eliminate them.
Yani
but if you are doing a kind of direct slicing, as you know, we don't have any triangles there. Without dealing with such triangles, checking the integrity, you can do the slicing. But in STL files, you cannot remove.
Yani kompleks bir parça olduğunda kendimiz hesaplayamayız o zaman. Anladım.
That's why I'm always using the or cube in our examples, in our questions.
Anladım, teşekkürler.
So what do we have beyond the STL file? As we discussed at the beginning of the course, beginning of the semester, we can set that. We set that instead of generating the STL files or some intermediate files, we can directly do the slicing on the CAM software. So this will save us time. This will increase the accuracy, and we will have more freedom. This will make our parts having high quality. And we can do it for having heterogeneous interior structures, since you know that once you convert your design into an STL file, it's always assuming that the interior is a solid one. We don't have any special structures interior. But if you do direct slicing, then it's quite easy by having the slices of the interior, such special interior structures. You can directly generate the G-code file or other machine files and have your part printed. And obviously, depending on the type of CAD software you are using, type of machine you have, there might be differences and you need to be careful about them. And again, beyond the STL file, we have these days some special color models like AMF, as you discussed, as you mentioned in your first homework. We have another one. I think this one is virtual reality model, language, something like that. And this type, let me show you a printer, a special FDM printer. Now I will be sharing the window. Yes, this is the company called Zmorph, and they can print colorful parts, as you see. And they have a different technology. And you see here, they have highly complicated products. And in order to do that in their software, the user should be able to define these colored regions. Otherwise, it will not be possible. So let's have a look at it.
Hello and welcome.
Do you see this full screen now?
Yes.
I think yes. So what they have a special nozzle. If you remember the conventional triple F nozzles, we have a single one, and it can only extrude one material, one color. But their extruder is a bit different. It combines two materials into a single nozzle, and with the help of this approach, they can print any color by the combination of two different colors. So you see, by using a single color, they print it white and green at the same time. Or if they have yellow and red, as you see, they can also print orange in between. They have blue and green there. So this is their novelty. So you see, they have a single nozzle, but the conventional two color or two nozzle triple F printers make use of it, two extruders. They have separate colors, and they simply, let's say, print yellow part first, and then clean the nozzle, and then print blue part with the other nozzle. But in their technology, they combine these filaments into a kind of a chamber, and then try to adjust the color by their computational algorithm.
Show you how to use it with our fertilizer software.
So so far, the computing part is the most important thing in here, actually. Since the STL files only have the surface information, they don't have any color information or texture information. So that's why they need to have such a special CAM software. And here you see they are going to edit all these surfaces, and it's quite time consuming. So you need to select some regions and then set the extruder for that region.
Click, right click for that, and you can easily preview each layer, even before we generate G-code, and generate the support by one click as well. Previewing the real G-code in 3D is very easy.
This is another option. As you see, they can import some images and directly reflect that image on the surface and try to color it.
So dual pro extruder is
so this is another nice product they obtained with their technology. Using yellow and red filaments, they could obtain orange color in their products. So let's go back to the slides. Any questions, guys, about this example?
Hocam bu dediğiniz teknoloji RGB gibi mi? Yani farklı oranlarda karıştırınca farklı renkler elde ediyoruz.
Yes, similar to that, but they have two, so we can say that it is RG simply. And as far as I know, there are some studies where they try to join 3 or 4 colors, and there's also a company called Palette, and I think they use 4 filaments at the same time. Let me try to find them quickly. Any questions while I'm doing some search on it?
Hocam bu Zimorph'ta tek nozzle vardı değil mi?
Yep, they have just a single nozzle. So now have a look at this product. This is a very special product, and you can use this one with any kind of triple F printer. And they can have any color. You see, this is their equipment. They connect 4 different filaments, and inside this box, they combine this color and try to have a single filament. Again, the computational part is quite complicated. According to your design, they will do some computation and try to determine in which part of your print you need to have, let's say, yellow filament, in which part you have blue. So the computation part is quite complicated, and it's about $600. And the advantage is that you can use it with any type of printers. And here you see that these are the tests they performed. This is the interior of their machine. They have different inputs, and then at some point, these filaments are combined. Not an easy task, but the output is quite nice. Here you see another, they have a second file, but not important right now. So if you are interested, you can have a look at the details of this company. Let's continue with the remaining of this chapter. As I have shown you, you also have the multiple material options, but the thing is that your software and your machine should have such capabilities. And in addition to additive manufacturing, we can also use STL files for other manufacturing operations like machining or forging, it doesn't matter. And they all also accept such STL files into their CAM software, and then you do little settings and start the manufacturing process. Now further, we have some other softwares related to additive manufacturing. I would like to show you some of them. These are some simulation software, and they are especially used for simulating some additive manufacturing processes. So this one is for metal additive manufacturing. So you do some simulations and try to see whether you have high quality parts or not. And Digimat AM is for SLS, and as you see, for FFF or FDM, I use this one. It's quite nice. You can obtain whether you are going to have any warpage or not, or you can guess the strength of your resulting part. So this is how they proceed. Let me show the result. So this is an example of SLS, but it doesn't matter. With the help of these simulations, you can try to actually get an estimate value about your resulting product, whether it's going to withstand to the forces you are applying on it or not. So these days, some companies are working on such software, and you'll have much powerful of them, I think, in near future. We may have further software on such issues, but they're not complicated. There might be software on estimating the build time, doing the machine setup in an automated manner. There are some software doing the monitoring. For instance, they have some thermal cameras, and they check whether the given or whether the additive manufacturing machinery is going well or not. And during this monitoring, you may see that there's a problem at the layer, and you may directly stop the printing and not waste your material. And there are also some software doing the planning in an automated manner once again, but we don't have any further. So this actually concludes the chapter.